Hi. So far, we built up a virtual world, but that virtual world is dead. In order to introduce life in our virtual world, we have to introduce motion, also called transformations. Ta pantarei, said Herakleitos, which means that everything moves and nothing stands still. And he was absolutely right. So we need transformations in virtual worlds as well, and without the redefinition of every single object in every point of time. In computer graphics, we also need transformation between different coordinate systems, which is not the typical interpretation of motion in our everyday lives. We have to transport objects from one coordinate system into another. Our objects are in the virtual world, and at the end of the rendering process, we want objects to be on the computer screen, which is a different coordinate system. So what are transformations? Transformations are nothing but point functions that assign a point to another point. If the points are described by Cartesian coordinates, we can say that transformations are functions that compute the transformed Cartesian coordinates from the original Cartesian coordinates. If we had just finite number of points, we would be perfectly satisfied with this interpretation. Executing this transformation for the finite number of points, we would be done. However, life is not that simple. In our virtual world, we have objects, and each object consists of infinitely many points. Obviously, it's not really feasible to transform these points one by one, since we will have infinitely many such transformations. We need to transform an object at once or at a few number of steps instead of considering each of its points individually. Recall that during modeling, we developed representations, formulas, and algorithms for every considered object type. For example, if we take the circle has the representation of a center point and the radius, and an algorithm that generates points on the circle using this representation. And this algorithm involves the sine and the cosine functions. Another example is the cat-Moorheim spline. Its representation is the finite number of control points, and its algorithm that creates points on the curve from the control points involves cubic interpolation between the subsequent control points. The problem is that if we apply a transformation for the points of these objects, both the representation and the algorithm are modified. For example, if we take the very simple transformation of scaling the object in the direction of x is x by 2, then this transformation, when applied to a circle, will result in another object, an ellipsoid, which cannot be represented by the center and the radius anymore, and our original algorithm developed for circles will not be applicable for the resulting object. So that's bad. So what can we do? We have to limit ourselves, both in the domain of the objects and also in the domain of the allowed transformations. We will use only those transformations which guarantee that line segments will be mapped to line segments and triangles will be mapped to triangles. This is enough because all curves can be approximated by line segments and all surfaces can be approximated by triangle meshes. If the line segments and the triangles are small, this approximation is accurate enough, so when they are comparable with the size of the pixel on the screen, nobody will be able to tell the difference. Let us realize that what we need is a transformation that maps lines to lines in the two-dimensional case and planes to planes in the three-dimensional case, because line segments are parts of a line and triangles are on a plane with line boundaries. So the crucial question is, what kind of functions T guarantee that a line will be mapped to a line? Let's pose the question differently. and ask what function t can guarantee that lines will be mapped to lines and parallel lines will also be parallel after executing the transformation. So such transformations that map lines to lines and preserve parallelism as well are called affine transformations. This is a very important group of transformations because all really important practical transformations belong to this category. For example, the translation. Obviously, if we translate a line, we will get a line. If we translate two parallel lines, the result will be again two parallel lines. The same applies for rotation, scaling, shearing, reflection, etc. So our first target is the set of affine transformations. I pose the question again. What are those functions t that map lines to lines and preserve parallel lines? Computers deal with numbers, so points to be transformed and points obtained after the transformation are expressed by coordinates. So in the background, we have a Cartesian coordinate system with two basis vectors, I and j, and in this way, based on the origin of the coordinate system, we can express every point in the two-dimensional plane by two numbers, the x and y Cartesian coordinates. The interpretation of the Cartesian coordinates is the projection of the point onto the coordinate axes. So along basis vector I, we have a vector x0, and along basis vector j, we have another vector 0y, and if these two vectors are added, we arrive at the point of interest from the origin of our coordinate system. These actors form a rectangle in a Cartesian coordinate system where the edges or the sides are just the two components. In the corner of this rectangle we have the origin, and in the opposite corner the point that is expressed by Cartesian coordinates x and y. We are studying the transformation that maps p to tp, or x and y to x prime y prime. But we know the geometric properties of this transformation, so let us examine how such transformation changes the rectangle formed by the point of interest and the axes of the coordinate system. The sides of a rectangle are lines. Affine transformations map lines to lines, so if we transform all points of this rectangle, we will have something where the sides are also lines and opposite sides have parallel lines, because affine transformations also preserve parallelism. Such objects are called parallelograms. So affine transformations transform rectangles to parallelograms. Let us express Tp, or x prime y prime, from the coordinates and basis vectors of this coordinate system. In order to reach Tp from the origin of the coordinate system, first we have to move to the image of the origin of this coordinate system. By image I mean the point that is the result of the mapping of the origin, or in Cartesian coordinates 0, 0, having applied the transformation. From this corner of the parallelogram, we should walk along this side of the parallelogram. This vector is the difference between tx0 and t00, where tx0 is the image of this point when the transformation is applied. And then we have to walk along the other edge. However, we know that parallelograms have opposite sides that are parallel to each other and also have the same length. So instead of walking along this edge, the same result can also be obtained by adding this vector to the point reached in the previous phase. This vector is the difference between tiy is the image of this point, and t00 T00 is the image of the origin. Putting these all together, we could express the transformed point Tp from the image of the origin and from the images of point x0 and 0y. The next question is how function t can depend on variable x. To decide that, let's assume that we multiply x by 2, so we add another rectangle of the same size as the original rectangle, so the new point will be identified by Cartesian coordinates 2x and 0. This new rectangle will also be placed somewhere by applying the transformation for its every single point. The image of the rectangle will be here. It's quite obvious that the edge of this new rectangle must be the continuation of the edge of the previous rectangle, because lines are mapped to lines by affine transformations, and here the two edges are on the same line, so after the transformation, the transformed edges must also be on the same line. Similarly, the top edge of the two rectangles are on the same line, therefore after transformation they must also be on a line. So there is no change of direction here or there. However, one question remains to be asked and answered. Can it happen that the transformed rectangle is shorter in this direction than the transformation of the first rectangle? To answer this question, let us consider the diagonals of the two rectangles. In the original setting, these green diagonals are parallel with each other. According to the definition of affine transformations, these lines must also be parallel after the transformation. But if the two parallelograms have different sizes, this would not be the case. So this cannot happen. The only reasonable choice is that the second rectangle, when it is transformed by function t, results in a parallelogram that has the same size as the first parallelogram. What does it mean? If we multiply x by 2, the transformation should result in a vector that is 2 times as long. We could do the same experiment with 3, with 0.5, with an arbitrary value and come to the same conclusion. So generally it means that the dependence of t on x can only be linear in order not to violate the assumption that affine transformations map parallel lines to parallel lines. And the same argument can be applied for coordinate y as well. So this is a linear function, which means that it can be expressed as x times t10, and this is also a linear function, which means that it can be expressed by y times t01. So let's do that. So that's our almost final expression for the transformed point. Let's do a little bit of bookkeeping. This vector is the difference of the image of 10 and 00, the origin of the coordinate system. Between 10 and 00, we have basis vector I in a Cartesian coordinate system. So here we can observe the transformed version of basis vector I. And similarly, this is the transformed version of basis vector J. As we have already concluded, this is the transformed vector of the origin of the coordinate system. So the transformed point can be expressed as the image of the origin and x times the image of basis vector I, called I prime, and y times the image of basis vector j, called j prime. Concerning xy Cartesian coordinates, this expression is linear in them. This expression can also be written in a matrix vector form. xy is extended by a one value in order to multiply the O prime variable with something, with 1 here, which is multiplied by a 3 times 3 matrix where the first row contains the Cartesian coordinates of the image of basis vector I. The second row contains the xy coordinates of basis vector j, and the third row contains the Cartesian coordinates of the transformed origin. If we put 0, 0, 1 in the third column of this 3 times 3 matrix, it is guaranteed that for an arbitrary xy value in the resulting 3-element vector, the third one value will be preserved. You may also recall the ambient space model of geometry, where vectors are extended with ambient coordinate 0 and points are extended with ambient coordinate 1. This is exactly what happens here. The transformed I is a vector, therefore its third coordinate is 0. J and this transformed version are also vectors, so they must be equipped with 0, while the origin and its transformed version is a point, therefore its third coordinate is 1. This matrix vector multiplication can also be rewritten in the following form, where A, B, C are the x coordinates of the transformed I vector, j vector, and the origin. D, E, F are the y coordinates of the transformed I, j, and the origin. We can see that the new Cartesian coordinates x prime and y prime are linear functions of the original Cartesian coordinates. So we can conclude that this affine transformation changes the Cartesian coordinates linearly, or can be expressed as a vector matrix multiplication where the 3 rows of the 3 times 3 matrix in case of two-dimensional transformations are the transformed I vector, j vector, and the transformed origin. So this proof was a constructive proof. We could not only prove that affine transformations are linear functions for the Cartesian coordinates, but this discussion also told us how to find the transformation parameters, including this 3 times 3 matrix or the A, B, C, D, E, F scalars in the transformation formula. It's enough to see what happens with the basis vectors and the origin, because these 3 components determine the 3 rows of our 3 times 3 matrix. Let us use this knowledge to find the transformation matrix for classical affine transformations. Our first example is the two-dimensional rotation, when points in the two-dimensional plane are rotated around the origin of the coordinate system. This is an affine transformation because lines will be mapped to lines and parallel lines will be preserved. So it can be done with a 3 times 3 matrix multiplication, where the first row of the matrix is the image of basis vector I if we execute the transformation. We have to examine what happens with basis vector I if we apply a rotation by angle phi around the origin of the coordinate system. According to the definition of the sine and cosine functions, when we rotate unit vector I, the rotated vector will have cosine phi as its first coordinate and sine phi as its second coordinate. The result is a vector, so the third component is 0, so we already have the first row of the matrix. To get the second row, we have to examine the image of basis vector j. So we can use the same argument, laying down or looking at the situation from here, where the role of the first vector is played by j and the second vector is played by minus I. In J prime, we can observe the cosine of phi in the J component, which is here. In the second component, we can observe the sine of phi multiplied by minus 1 because the second vector is minus I. So indeed, we will have minus sinus phi, cosine phi as the image of basis vector J. When we are rotating around the origin remains there. This is a so-called fixed point of the transformation, so the image of the origin will also be the origin. In Cartesian coordinates it has 0, 0, and it's a point, so its search component is 1. And we are done. This is a 3 times 3 matrix that expresses rotation. So whenever we have a point with Cartesian coordinates x and y, we extend it with a 1 value in order to express that this is a point, and this row vector is multiplied by the 3 times 3 matrix to get a 3-element vector that represents the transformed point, which is just the rotated version of the original point. The second example is three-dimensional translation. So now we have 3 Cartesian coordinates that are extended by a 1 value in the ambient representation, so we will transform 4-element vectors. The transformation matrix is also 4 times 4 matrix, where the first row describes what happens with basis vector I, the second row what happens with basis vector j, the third row what happens with basis vector k, and the fourth row what happens with the origin of the coordinate system. When we translate, a vector doesn't change, so I will also be I. In coordinates I is 1, 0, 0, 0, which remains in I prime as well. J is 0, 1, 0, 0. J is not affected by the translation, so the image of the transform J will also be 0, 1, 0, 0. Similarly, K prime will be the same as K in coordinates 0, 0, 1, 0, but translation modifies the origin of the coordinate system. So from 0, 0, 0 in Cartesian coordinates, the origin will go to the end of the translation vector, represented by vector v, or considering its 3 Cartesian coordinates vx, vy, and vz, and it's a point. So when translation needs to be executed, the Cartesian coordinates of a point extended with a 1 value should be multiplied by this 4 times 4 matrix. We will often need scaling operation as well when scaling is executed along the 3 coordinate axes, assuming that the fixed point of the scaling is the origin, so the origin remains in its original position. If we scale along axis x by a factor of sx, basis vector I, which is originally represented by 1, 0, 0, 0, will be transformed to sx 0, 0, 0. So this is going to be the first row of the transformation matrix. Similarly, if the scaling factor along axis y is sy, from j, which is 0, 1, 0, 0, we will get 0, sy, 0, 0. In the k or z direction, the transformed k vector will be 0, 0, sz, 0, and finally the origin is not affected, so the fourth row of the transformation matrix will be 0, 0, 0, 1. These were pretty simple affine transformations. Let us consider a more complicated one, rotation in 3D. Assume that we are rotating around an axis d that goes through the origin of the coordinate system, and we also suppose that the direction of the rotation axis is specified by a unit vector. This assumption will simplify our formulae. So we are looking for a formula for rotation, which means that from position vector r, a new vector r prime is created that represents the rotated version of r around axis d with angle phi. The origin of the coordinate system is here. First of all, let us decompose position vector r into 2 components. One is parallel with axis d and the other is perpendicular to it. The parallel component can be obtained by projecting position vector r onto axis D. We know that the dot product is nothing but a projection of one vector onto the other vector. So if D is a unit vector, R dot D expresses the length of the projection. If this scalar is multiplied by the unit vector D, we will get a vector which is nothing but the projection of R onto axis D. We call it R parallel because this is the parallel component. This parallel component doesn't change when we rotate around the axis because it is in the axis, so the rotated version of the parallel component will be equal to the original parallel component. The other component of position vector R is the perpendicular component, and we will denote it by R perp. How can we get the perpendicular component? Well, it's pretty easy because we have the original position vector and we already computed the parallel component, and the perpendicular component is just the difference of the position vector R and the parallel component. So from R we subtract the projection which has already been expressed in this form. When the vector is rotated around axis D, this perpendicular component will stay in the plane that is perpendicular to the axis, and its transformed or rotated version will have angle phi with the original perpendicular. So we need a formula that expresses the rotated version of R perpendicular, and this rotated version is denoted by R perpendicular prime. It would be rather easy to express this rotated perpendicular component if we had another vector in the same plane where R perpendicular and R perpendicular prime can be found, and this additional vector is perpendicular to R perp. This vector is denoted by R perp perp because it is perpendicular to R perpendicular. So how can we get it? This vector is perpendicular to R perp, and it is in the plane that is perpendicular to the axis. So we have two vectors, the axis and R perp, and we are looking for a vector that is perpendicular to both of them. The operation that produces a vector that is perpendicular to two other vectors is the cross product. So using the right-hand rule, D cross R perpendicular points into the direction of the interest. And not only the direction but also the magnitude of the vector is correct, because D is a unit vector, R perpendicular has some length, so the resulting vector of the cross product operation will have the length that is equal to the length of R perp multiplied by sine 90 degrees, which is just 1. So this R perp has the same length as R perp. So both of them are on a circle where the rotated vectors are pointing to. With R perp and R perp, we can express the vector that is the rotation of R perp with angle phi. Because here we have a right triangle, so the two components of this black vector are R perp multiplied by cosine phi and R perp multiplied by sine phi. One additional remark: we expressed R perp as a cross product of D and R perp. We can simplify this and replace R perp by R, because R is the sum of R perp and R parallel, but R parallel is parallel with the axis D, and when we obtain the cross product of two parallel vectors, the result will be 0. So adding R parallel to R perp doesn't make any difference in the result after the cross product. So we have computed the rotated version of the parallel component, which is the same as the original parallel component, and the rotated version of the perpendicular component, which will be the new perpendicular component. So the rotated vector will be the sum of these two parallel and perpendicular components. Basically, we are done. We have to do a little bit of bookkeeping and put the partial results together. So the rotated vector is the transformed parallel component, which is equal to the original parallel component, which could be expressed in this form. This is here. The perpendicular component multiplied by cosine phi and r perp multiplied by sine phi. And we replace r perp and r perp by their respective formulae. We often rewrite this formula by grouping the terms that contain this d multiplied by the dot product of r and d. This formula is called the Rodriguez formula. So when we need to rotate a point around an axis that goes through the origin, but the direction of this axis can be arbitrary unit vector d, then we can use this formula to find the result. However, instead of the formula, we need a matrix that does the job. So how can this formula be converted into a matrix multiplication? If we have a formula and we have to convert it to a matrix multiplication, we need to consider the basis vectors and the origin separately, and they will define the 4 rows of the 4 times 4 transformation matrix.